Hey, making another video presentation, draft physics and such. Yeah, different intro. It's a really good one, right? Yeah, I like it too. Anyway, I figured I'd do a comment first before we get to some more Feynman stuff. Just because it's just so funny. So Feynman uses as an analogy in the video I just did in the previous episode. Analogy of us getting it wrong was this idea that we had this understanding of simultaneous, and it's just, and then we found out about this general relativity, special relativity, and it changes everything. So he's using it as an example of how something changed, right? Because of. Now, obviously, for like at least thousands of years, many thousands of years, people have known that if I'm throwing a rock at somebody, the closer they are, the sooner the rock gets there, right? So we've all known that for a long time. If some event happens, it happens to the person closest to the event sooner. Like if the bear's coming and it's going to just swat people, the people closer to the bear get swatted first. Yeah, duh. So that was our understanding. All right, so and somehow special relativity and general relativity change all that, and it's, so that's the real context here, But he says, sorry, draft physics, but the lack of simultaneously in special relativity that Feynman opens up with, he opens up as an example of how we had this wrong perception. That we were getting it wrong somehow, that somehow we didn't understand that if you're closer to an explosion, you know about the explosion sooner. Yeah, we didn't know that. We had it wrong. Okay. Opens up with concerns two observers moving, WRT with each other. But really, again, where do we need special relativity to know observers have different points of view? That's not the question. The question is whether time changes. Whether the two things didn't really happen simultaneously because two observers disagree about it. That's the real question. And if that didn't change, then nothing changed. We didn't need Einstein's theory at all then. If all he's talking about is people know about things at different times, well, we don't have a problem, do we? The problem is he's saying time changes. No, that doesn't happen, you idiot. Okay, and and it is real because light always moves at a constant speed for everyone. No, it always moves at a constant speed, period. And it doesn't move at the same speed for everyone. So again, this is an idiotic argument. If, again, you're moving the same speed or almost the same speed as the light, the fact is it'll take many centuries for you to perceive it to move the same speed. It will literally, the universe will be billions of years old before you see it moving the same speed. So that's just a crock of shit. Okay. The fact is, if I move towards something, I know about it sooner. And if I'm moving towards a beam of light, I'm going to have an interaction with it sooner than I would have if I wasn't moving towards it. And that's just a fact. And if I'm moving away from it, I'm going to have an interaction with it a lot later. And that's the reality. Nothing in reality changes. You're arguing that somehow we don't know that we perceive things at the speed of light. Well, of course, that's what we do. We don't perceive things instantaneously. So what? How does that change time? I mean, this is just such a stupid fucking argument. Ugh, pathetic. Fuck off. All right. I mean, I played the clip. He's sitting there using it as an analogy how somehow we needed Einstein's vision to understand that stuff doesn't happen. We don't perceive things instantaneously. Yeah, we did have that one right. We already knew that. Everybody already knew that. So unless you're saying something else, Einstein didn't change the world any. Didn't change reality one stinking little tiny bit. All right, anyway. So we're continuing with Feynman and the two-slit experiment.
X. It means only you move the doggone thing up and down. All right. Now, first, I would like to make a few modifications from real bullets into idealizations. The first is the machine.
Okay, so let's understand. So he's going to try to explain a phenomenon by jumping from electrons to photons to waves, in water to, and saying they're all the same thing. That somehow they're all behaving the same way for the same reasons for the blah blah blah. And right there, I mean, why would somebody assume that it's all for the same reason? Except to say it's magically random. The same demons are doing it. It's, whatever similarities there are, they're subtle and they need to be understood as individual objects having very different interactions with the world. It's almost, this is a proportional thing, right? I mean, the heavier a rock is, it'll fall down a cliff very differently. The more mass you give it, the more less and less it does this little bouncing thing and all that kind of stuff. And so, yeah, the idea is they all fall, but they all fall very differently. And yes, they all have some effect, but they have effect proportional to their size, and that's what's clearly indicated by the evidence. When they do this experiment with bigger objects, the results aren't at all, clear and decisive. They're all fuzzy and barely there and that kind of thing. So it's clearly an effect that's affecting all these objects, but it's affecting them for different reasons, different mechanics, because of their differences.
The machine gun is very shaky and wobbly, and that the bullets go in various directions, not just exactly straight on and bounce back.
Right. See, if we had bullet shooters, if we had some mechanism that could actually shoot these things straight, then we would find out that this has nothing to do with what they think it has to do with, because you could just aim them and shoot through slits and see exactly what they do.
And they can ricochet off the edges of the...
Well, the catch is you can't see exactly what they do because only pieces of them end up in some place. And again, this is about putting pieces back together again. And that's the big reveal. That's the big fact they're missing, is they have no understanding that photons are a thing, a composite object. I'll just draw it real quickly to make the print. Oh, there's cords everywhere. See, they think a photon is this. There's a photon, okay? And it's not. Photon is made of what they call their quanta. There are these little bits of energy. And the fact is, and this is their frequency, and they have a polarization which is out of alignment. And the fact is you can disturb this pattern by breaking it into pieces. Two pieces that are here, and you can have these two pieces now that have been changed in space. So these two end up here, out of phase with these two pieces. And now neither one of these can be seen as a photon because it's not a ray long enough. It doesn't have enough length to be seen as a photon, but it's still energy. And the simple fact is the very mechanism you use to do this, to take it from here and put it over here, you can use that very mechanism to sit there and take this and put it right back over here, and so then you can put it back together again. So the idea is that what we see in the experiment isn't, you can't just see what happened, because when we break the photon by putting stuff through a slit and you break pieces off, these pieces individually won't be seen. So if you do the single slit, one photon at a time, you might not see anything. You'll see photons arrive here, but all the ones that get scattered are pieces. And you really won't see them unless you have another photon at the same time hitting the other surface. So if something else doesn't hit this surface, you won't see what hit this surface. And it's only when you line up those two things that you can see the photon. And I've sort of explained that the two slit experiment is really 4 vectors. Okay, you're talking about a string with big notches on it coming off this little distance, and then you're talking about a string with little tiny notches on it. Okay, that's off this 2 distances because there's lots of wavelengths in here. Okay, and we're really just talking about lines. We're talking about the length of this line versus the length of this line. And that's the big difference in the length of that line, and the number of frequencies will dictate. So if you just put a nail in here and a nail in this one, and you move them to different locations on this arc, you'll find locations where the notches line up, all 4 notches, all 4 strings, it's right on a notch. And it's all 4 strings are on a notch, all 4 strings on a notch. And those are the places that'll be lit up in the experiment. Because you need the contribution from both, the pieces from both, to be able to see the the object brightly, much more brightly. So you can do the experiment where, yes, there's a little bit of fuzz in between here. The darks aren't completely dark because both patterns are still visible. That is, two contributions make enough light that you'll see it. So this is making a contribution that you'd still see, and that's when you get a pattern that's a little bit fuzzy. That is, the darks aren't completely dark. The brights are brighter, okay, and then the darks aren't quite dark, and then the brights are brighter. But the more contrast you get between the darks and the brights, it means that you have low enough light coming into the experiment where all four contributions are needed to actually make a photon, to have enough pieces that you're changing the phase of by changing the distance they travel, and you're putting enough pieces back together to make a complete photon. That explanation completely explains the phenomenon. Completely. It's a complete answer. Their answer isn't close to complete, nor is it reasonable. This is completely mechanical. Their explanation is completely unmechanical. So even though they call it quantum mechanics, it doesn't have any mechanics in it.
The holes in these armor plates. And finally, well, let's say, for instance, that the bullets have all the same speed or energy if you want, but that's not very important. But the most important idealization in which it differs from real bullets is I want these bullets to be absolutely indestructible.
So let's understand. See, he's talking about the photon. He's using this as an illustration of what a particle photon would be. It would be a single bullet. And that's not the theory. Photons aren't single bullets. Single bullet doesn't have a frequency. Single bullet wouldn't make any sense. So clearly photons are a thing. And they already know this because they know our eye doesn't detect photons unless there's a certain amount of ray length to it. And their frog sees a photon that's made out of fewer bits. And that a photodetector detects photons even smaller ray length. I mean, those are pretty hard facts.
So that what we find in the box is not pieces of lead of some bullet that's broken half, but we get the whole bullet, please. So imagine indestructible bullets, or hard bullets and soft armor plate or something.
Right, so these are all what he's saying the experiment is confined by. So when they say something like it violates Bell's inequality or something else, or there's no hidden variable, well, that's because they've had this assumption built into what they're arguing that somehow you can't break a photon and then rebuild it again. So that's already their argument. See, if they said, well, what if bullet pieces break off and they go at funny angles? And what you really measured was how many pieces of a bullet you collected, how much energy you actually collected. So you could get a piece off one side and a piece off the other side at the same time at a location, and the two pieces would add up to a bullet. Well, then you could understand how hard bullets could make the pattern.
And now the first thing that we will notice about bullets is that the things that arrive come in lumps. When the energy comes, it's all in one bullet full of bang. If you count the bullets, there's 1, 2, 3, 4 bullets.
Right. So when we know that even with photons, this isn't true because you can turn the sensitivity of a detector, a mechanical detector, you can turn it up and down. You can make it more and more sensitive and less sensitive. And that the more sensitive you make it, it starts to see photons that you can't see, that you don't think are there. So, I mean, another confinement to how the experiment's done and how it's illustrated that doesn't have anything to do with what they know to be a fact. They've just established it somehow as a fact, that photons don't break into pieces and that you can't recombine them.
The things come in lumps. They're equal in size, we suppose, in this case. And when a thing comes into the box, it's either all in the box or it's not in the box.
So it is, in fact, either a photon you can detect or not a photon you can detect, but how it got there, out of what pieces, that's an open question. I think it's open in terms of an argument against their theory, and clearly closed as a brilliant argument against their theory and proving the alternative mechanical theory.
It comes in lumps. More. If I put up two boxes here, I never get two bullets in the boxes at the same time. Well, if the gun isn't going off too fast and I have enough time between, you see, slow down the gun so they go off very slowly. Bing, 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 bing.
Right. Now, if they actually did that experiment correctly, that would point out to them that, oh, the pattern does disappear. There is no pattern anymore. Because really what's happening is that you do need the sources. In a double slit experiment, you need all four sources. And one photon can't hit all four sources. It can't make pieces at all four sources. So you obviously need more than one photon going through the experiment at the same time or near the same time. Obviously they have some phase difference. So, the photon that's going slower can go in earlier, and the photon that creates the back end of the photon can come in later. But the time would be very, very close to each other, quite obviously, within a nanosecond. Yeah, you need the pieces. So you need more than one photon. A real one photon at a time experiment won't create the pattern. This won't happen.
Then put the two things here and look very quickly in the two boxes. You'll never get two bullets at the same time in the two boxes because a bullet is a single identifiable lump. I call that characteristic of the object that it comes in lumps.
So again, it's an agreeable statement. It comes in lumps, but photons aren't lumps. They're clumps. Okay, so instead of a lump, they're a clump, a collection of lumps. All right, so, but it's a subtle difference, but it's all the difference. This is exactly why they got the physics wrong. Is because they keep thinking in terms of a photon as a static thing. This is a photon, it's a thing. When a photon is a composite object, and depending on how you make the composite object, the photons can be different in the sense that the ray length can be different.
So the first thing about bullets is that they come in lumps.
They're received in lumps is the other counter argument to that statement. The only way we can see them, the only way we know it's a photon is because a certain amount of energy hits a collection of atoms and those atoms react in a certain way, giving us an indication that something exists. We can't measure anything smaller than the amount. So let's say the ray has, say there's a ray that has 70 of these little bits in it, that's got 70 of them. And say when we see 6, that's when the atom reacts. That's when our eye reacts, for example, and says photon. Well, then it's just going to say, well, then another photon hit right after that, and another photon hit right after that, and another photon hit right after that. It's just going to count them as individual photons of 6. Whatever the minimum amount is our detector needs, it's just going to break that ray into a sequence of photons, a sequence of energy that hit a location that caused an electrical effect. So again, our detectors are what's clumping it. We don't have any other way to see it. Well, we perhaps do have another way to see it as energy, as heat, but they don't bother attempting to detect the temperature profile that's coming out of the slits.
And now what I'm going to measure is how many bullets arrive here on average in a long period of time. So you wait an hour and you count how many bullets are in the can, in the sand, and average that. Now, we call that, if you want, let's say we take a definite time like per hour and say the number of bullets that arrive per hour. And sometimes you could call that what's called the probability of arrival, because it just gives a chance that a bullet going through this thing.
So again, this is almost like the relativity argument, in the sense you could call it that, a probability. Well, we know it's not a probability. We know the photon goes through this thing, and made a mechanism, and it ends up in a location, and there was nothing probabilistic in it, in the raw sense of what it's doing, the function. And the probability is, where did the photon go through the slit? That's the probability. Did you go through the middle? Did you go through the edge? Did you go through here? That's the probability, is in the gun firing the photons erratically. But that's all there is. There's no magic about it. So he's just talking statistics. So again, their math is just statistics and just ways of analyzing statistics. And they're saying, well, because we have a really good formula for analyzing statistics, therefore we predicted why photons react differently when they go through different areas of a slit.
Arrives in this particular box, and this is proportional to the chance. One way to measure is to measure the average number of bullets that arrive over a period of time. Now, the number of bullets that arrive in this box here will vary.
So again, they didn't predict the probability. They watched it and observed the probability. So again, when they say they predicted something, they didn't predict anything. They observed it and quantified the observations, formalized the observations. No magic here, no prediction, no power. The power to know what you already know, well, that's not much of a power. The power to say it a different way, I mean, that's not much of a power.
As I vary x, and I'm going to make a graph here in which I plot horizontally the number of bullets that I get if I hold this thing here for an hour. And I'll get a curve that will probably look more or less like this. Because when the box is behind one of these holes.
So he's using bullets as an example. So yeah, you might figure the two slits have to be kind of a little bit apart from each other. But again, the two curves wouldn't be like that. Projected wise. So again, it's a wrong description because the slit width is going to be tiny compared to the distance of the target. And he said that when he set up this drawing. He said, oh, it's a very far distance apart, and this is a very far different distance away. But it's not going to change the trajectory of the bullets. The bullets were attempted to be fired straight. That's what the whole first hole was meant to do, is to have them move straight towards the pattern, towards the slits. So again, it wouldn't be two humps. There'd be two humps right on top of each other, merely separated by the distance that you have between the two slits. And that would be that distance would translate to the same distance. It wouldn't be amplified or magnified. So there wouldn't be two humps. There'd be two humps right on top of each other here in the middle.
It gets a lot of bullets. The ones that went through this hole, and otherwise it gets them that went through this hole. And if it's a little bit out of line, it doesn't get as many. They have to bounce a little off the edges of the hole. And so it disappears like this. And this is the number that we get in an hour when both holes are open. And I call that, by an abbreviation, N12, which merely means the number which arrive when hole number 1 and hole number 2 are both open. Looks like that, sir. Now, I must insist that the number that we're plotting here isn't...
So you could understand that if this was pieces of something going through, you could understand that the more sources, the more things you could put together. So it magnifies the effect. So obviously you could understand that the two holes being open, when one hole is open, you get a certain number of parts that you only get from two sources. But adding two sources multiplies how many parts you can put now, how many things you can put together. And so you would expect there to be a difference. When one hole is open, when the other hole is open, it's not just merely a plus thing, it's a multiplication thing. You're magnifying the capacity to put pieces together.
It doesn't come in lumps. You can have any size it wants. For example, there can be 2.5 bullets in an hour. In spite of the fact that the bullets come in lumps, what I mean by 2.5 bullets in an hour is that if you run a long time, like 10 hours, you get 25 bullets. So it's on the average 2.5 bullets. The N can have any size. It doesn't have to be in lumps because it's an average. I'm sure you're all familiar with the joke about the fact that the average family in the United States seems to have 2.5 children. It doesn't mean that there's a half a child in any family, whatever. The children come in lumps. But nevertheless, when you take the average number per family...
You need jokes. Jokes make physics better.
It can be any number whatsoever. And so this number N, which is the number that arrive in this container per hour on the average, need not be an integer. It can be a tenth, which would mean under those circumstances that you have to wait on the average 10 hours more or less per bullet. So what we measure then is the probability of arrival, which is a technical measure, the probability of arrival.
No, you measure the number that arrived. So again, it's just more playing with words. Okay, you're not measuring the probability, you're measuring the actual number. And you can call that a probability, but it doesn't matter because that's not what you measured. You measured the number that arrived.
There's a technical term, really, for the average number that arrived in a given length of time. And now, finally, if we go to analyze this curve N12, we can interpret it very nicely. We can interpret it as a sum of two curves, which I will draw here. You see, that's why I need the blackboard, so I got several cases. So I draw two curves here. One which would represent what I call N1. The number which will come if hole number 2 is closed by another piece of armor plate in front, and so they all come through number 1. And N2 would be the number that come through hole number 2 alone. So N1 is the number that...
So again, this is such a gross exaggeration of any difference in where they would be located. So especially in the light experiment, this wouldn't be your results. And these two would be superimposed in the same space. The slits are, less than a millimeter apart, and obviously when they're projected, there won't be any reason for them to spread any further apart, so they'll still be less than a millimeter apart, and so the drawing is deceptive. It's inaccurate. It's not describing reality.
Come to hole number 1 alone, and N2 is the number that comes to hole number 2 alone, those numbers being determined by closing the respective holes. And then we discover a very important law, which is that the number that arrived with both holes open is the number that arrived by coming through number 1 hole, plus the number that comes through number 2 hole.
Right, so this whole thing is dependent on you believing that photons are solid things that don't break and that don't have their phase, just part of their phase broken and then have their phase reconstructed. So there can't be pieces of a photon that go through that we don't detect. And that if we get pieces from the other slit, that we would detect those photons because now they're reconstructed. So there's a simple explanation that explains why it's not merely N1 plus N2. It's more than that, because there's lots of pieces going through N1 and lots of pieces going through N2 that you'd never see independently. But if you combine those two sources, there's lots of half a photons and half a photon that now the phase will be correct and now you will see them. So it's not just merely N1 plus N2. It's incorrect.
And this proposition, the fact that all you have to do is add these two together, I'd call nice, or no interference. That is, what you get from the two holes open is the same as you get by simply adding each hole separately. That's the bullets done. We're done with bullets.
So no point in calling an addition no interference, right? I mean, that there's complete lack of continuity there. The fact that it's not just 1 plus, A plus B, that A and B are both sending stuff, that doesn't mean anything until you put both the A part and the B part there. You have to have both ingredients to make the thing work. So, but there's no point in saying the word interference. What does that have to do with it? You don't know why. We're assuming we haven't gotten to the cause of the effect. So why say the no interference there?
All right, I begin again. This time with water waves. Here is standing some kind of a big mass of stuff which is being shaken up and down. This is a long line of barges or jetties with a gap in the water in between. Perhaps it's better to do with ripples than it is to do with big ocean waves that sound more sensible. Wiggle my finger up and down here, and I have a little piece of wood here, and ripples start out here, and then I've arranged in a tank to put boards in the way here so that I have these two holes. And then I have this so-called detector, and then what I do with the detector, what the detector detects is how much the water is jiggling. For instance, I put a cork in the water and measure how it moves up and down.
So it's a completely different effect. Obviously, you're not collecting an amount of something or this, or it's a completely different thing. The wave is going up and down or the wave is quiet. Completely different than receiving photons, not receiving photons. Yet they'll say it's exactly the same cause, the same mechanism, the same everything. It's this random thing. He's almost implying that, right? I mean, it's almost to say we know that water waves aren't doing that, that there's an actual physical reason why they make two waves when they go through. When the one wave goes through and it makes two little waves at the two locations, we know there's physical friction reasons that are creating the new waves. But we don't believe that when it comes to what's happening with photons or electrons or anything else.
And what I'm going to measure, in fact, is the energy of the agitation of the cork, which is exactly proportional to the energy carried by the waves. Also, I forgot to say that this jiggling is made very regular and perfect, so that...
Okay, so that's to the Farley kind of liars and the Puro kind of liars. This jiggling is made very regular. Okay, it's not no phony jiggling, no noise jiggling. Really straight, plain waves going in. It's clearly, at least Feynman, it doesn't have that much lack of integrity to say, yes, do the experiment with noise. So I'm just emphasizing that just for those assholes who think it's a good argument to say, yes, you're supposed to do the experiment with noise waves. No, you're not. Let's just play that again, just so it's clear.
It detects is how much the water is jiggling. For instance, I put a cork in the water and measure how it moves up and down. And what I'm going to measure, in fact, is the energy of the agitation of the cork, which is exactly proportional to the energy carried by the waves. Also, I forgot to say that this jiggling is made very regular and perfect so that the waves are all of the same spacing from one another. And then I'll describe what we get under those circumstances.
Yeah, so he emphasized it. He said, oh, I forgot to mention this. It's kind of important that you use regular plain waves. So just to make sure it's pointed out.
For that, I first remark, well, let's see. First, we can measure the energy of the cork, but then another thing is important for light, for water waves, for waves. Water waves. Is that the thing that we're measuring can have any size at all. We're measuring the intensity of the waves or the energy in the cork. And if the waves are very quiet, if the fellow over here is only jiggling a little bit, then there'll be very little motion of the cork, and so on. No matter how much it is, it's proportional. So can have any size.
So you can understand that's a big difference, right? Because with photons they could do that, right? They could say, how long is the ray, of photon. But again, as the ray gets longer and longer, it just subdivides the material seeing the photon, just subdivides the photons. So breaks them into pieces. So, but we know that there's this difference between what a frog sees and what a human sees. That photon just can't be used as a term all by itself and you say they're all the same. Yeah, they're made of all the same stuff, but they're not all the same.
It doesn't come in lumps. It's not all there or nothing. And what we're going to measure is the intensity of the waves, which could be precise if you want, is the energy generated by the waves at a point.
Right, and we don't have a device that can measure this energy by itself, like a wave. We can't measure this little bits. We can only measure when there's enough of this stuff to call it a photon, enough ray length. So we have a limitation in that what we can measure. And obviously with waves it's a different experiment because you can see the pieces in waves, or you can't see the pieces in photons. The two travel completely different, and the whole mechanism is completely different. So there's no point in me, I suppose, emphasizing this point, because physically photons are doing something very different than water atoms.
And now what happens if we measure the intensity, which I'll draw on a third curve here, which I'll call I to remind you it's an intensity and not a number of particles of any kind, and I1, 2, when both holes are open, is a curve that looks something like this.
So he does draw it wrong, but it doesn't really matter. I mean, wrong in lots of ways. But all right, let's understand. He's not going to draw the two-slit pattern. He's going to draw a two-slit pattern you can only get if these little two holes are so small, right? The only way you can not get the right pattern is you have to make the difference in distance so small that the difference in the line difference, that you can't perceive it, that it's so small that it won't be perceivable in the pattern. So as I've drawn the experiment, what you're really doing is you're just comparing the length of lines. So you could, this line, this distance is two lines, right, to the same equal point. What we'll say some arbitrary point in space, doesn't matter. So these two lines are a different length, and then these two lines, okay, end up being a different length by an amount. And the point is, if I make these slits really, really tiny, okay, then this line difference becomes the same as this line difference. So you'll end up with the same number of notches on both rulers. Okay, so there won't be two patterns. There won't be an envelope pattern and then your bar pattern, because they'll all have the same size. The bars will be all the same. The bars being created by these two sources will be the same as the bars created by these two sources if they're really close, right? These two sources will end up having bars that are so close in size that you won't have any difference. But this requires very small slits. And any slit, reasonably sized, you'll get both patterns. You'll get the bars inside the envelope. Right. So Feynman doesn't do the real pattern. He does a pattern that is the abnormal pattern, the aberrant pattern, the special pattern, the pattern that doesn't happen routinely in the two-slit, which is you see both patterns. He does the pattern you'd only see under one specific circumstance.
An interesting, complicated curve, which ought to be symmetrical. Didn't do too badly, actually. It's a very complicated looking curve. That is, if we put the thing in different places, we get a very, very different intensity, which varies very rapidly in a peculiar manner. And you're probably all familiar with the reason for that. The reason is that the ripples, as they come out of here, have crests and troughs spreading from here. And they have crests.
All right, so he's saying it as if it's the reason. He doesn't believe in that, okay? He believes in it for water waves. But when he's going to apply this theory to photons, he doesn't believe they're waving and doing this waving interfering. He believes that they've been randomized by the magical Feynman god. And so anyway, so in drawing it this way, this is again a 200-year-old way of looking at the experiment and an analysis, and it's just plainly wrong. They can't make what Feynman's drawing right now is he's saying there's waves created here and waves created here, and he's saying this is analogous to the photon experiment. That's why he's explaining all these experiments and saying they're all the same thing and they're all created by the same phenomenon and all this. And what is so this is the Young experiment. You just do this all the way out, and what you'll end up with is these little patterns will show up as locations. You know, it'd be all zigzaggy here and zigzaggy here and zigzaggy here, and those locations will have these bars. Now the same truth applies that this should be viewed on a screen where they're equal distant, and then you'll understand that there's only a certain number of these little zigzaggies. Okay, there's not an infinite number of them. But this doesn't work. It won't create the double pattern. It won't create the, bar, 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 then nothing, then bar, 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 and then nothing, then bar, bar, bar. It won't create the right pattern. So, and it can't be made to create that pattern. There's nothing you can do to these two waves to make it work. It won't ever, ever, ever create the right pattern. Now, they keep talking about it as if it's such nail-in-the-coffin evidence. Well, how can this be nail-in-the-coffin evidence when it doesn't get this right at all? It doesn't see these two dark spots. It doesn't explain any mechanism to create these two dark spots. Two waves can't be made to make this pattern. You can't configure them in any way. You can't do any math on them. You can't do anything to them except move them to some location that is preposterous. So if I move them to here, and I make 4 of them, and I move it to here, and I move the wave to, invert it up, and I move this wave to here. So if I create 4 waves, okay, in places that would be impossible, so just imagine those flipped up this way. So if I make 4 waves, 4 centers, wave centers. This is about wave centers, by the way. Okay, when they put their 2 waves here, it's really just about these waves being a center. Then the math will work. So if I make 4 of them, okay, and I put them in places no wave would form, it works. And why does it work? Well, yes, because I'm putting them where the surfaces are, because the surfaces are the actual cause of the effect. The surfaces are the point sources. The wave centers are on the surfaces. Where the surfaces are located. That's the correct answer. The end. Two-slit debunked. Feynman was wrong. He didn't really understand, just as Einstein said 2 years before his death, I've been studying photons for 50 years and I haven't improved my understanding one iota. They had no understanding of photons. They still don't have any understanding of photons. They don't understand the mechanism and how it works, and they keep pretending they have a perfect model that is fundamentally and catastrophically flawed. It doesn't explain the pattern at all. There's no video on YouTube explaining these two patterns with waves. There's no drawing of waves coming out of the experiment that create these spots. Waves can't do it. It's impossible.
And trough spreading from here. Now, if we're at a place which, say, is exactly in between these two things, so that the two waves arrive at the same time, the crests will come on top of each other, and there'll be plenty of jiggling, which is the exact opposite of this curve. So I'll have to put, there should be another bump.
Well, obviously his drawing was terribly flawed, right? I mean, this isn't centered on these two slits, and so this, what he drew here isn't centered. I mean, it's pretty poorly done, actually.
We have a lot of jiggling right in dead center. On the other hand, if I were to move to some point here, since I'm further from hole 2 than hole 1, it takes a little longer for the waves to come from 2 than from 1. And when 1 has a crest arriving, the crest hasn't quite reached there yet from 2. In fact, it's a trough from 2. So the water tries to move up and it tries to move down from the influences of the waves coming from the 2 holes, and the net result is it doesn't move at all, or practically not at all, and so we have these low bumps at that place. And then if you move still further over...
Right, so this is the implication is that somehow the photons interfere with each other and that they annihilate in some bizarre way where they hop to the other locations, because obviously the other locations are going to be brighter. So, you know, it doesn't make any sense, you know.
Well, you get enough delay that when a crest is here, this other crest is in fact one whole wave behind. So in fact, it's a crest that is, two crests are coming on top of each other, but not the same crest, so to speak. The fourth.
So that would just be where I pointed out that you can have these two photons that are out of phase, and if they're out of phase by a certain amount, that is, they even arrive at the location, the slits, out of phase. Well, if one of them goes this way and one of them goes this way, there'll be different distances, and therefore the ones that were out of phase will be combined into a photon that is in phase.
Crest from here and the fifth crest from there on top. So you get a big one again and a small one, a big one, small one, depending upon the way the crests and troughs interfere, as we say. The word interference, again, is used in science in a funny way because we'll have what we call constructive interference. When they both interfere here, it makes it stronger. Well, they call it interference anyway.
So, yeah, that makes just no sense, that somehow two photons come together and you get a 4-photon. Somehow you get a photon that's more powerful than the two individual photons. That only works as a parts theory. Again, if you think of these as pieces, you understand why that happens.
But the very important thing is that I12 is not the same as I1 plus I2, and we say it shows interference. Yes, interference.
So that's the key point, is that they're saying because this is not just an equation where you can just say what's coming from one is the same as what's coming from two. There's obviously components, and those components add in a way that's multiplicative rather than just mere addition.
That's a funny term you use. Construct.
I mean, even if you thought of feet going through one and heads going through the other, you could understand that you can't make a thing that has feet and a head unless you get a contribution from both at the same time. You have to have both to make the, whole.
And destructive interference. I didn't mention what I1 and I2 look like, but we can find out by closing this, for instance, to find I1. The intent.
So they also draw this like these are absolute zeros here or something, and that's the whole point. Is depending on how you do the experiment, you won't get absolute darks between the bars.
That you get here, if the hole is closed, is simply the wave from one hole for which there's no interference, and that's this curve. N1 is the same as I1, and the same way otherwise I2, and this curve is quite different than the sum of these two. As a matter of fact, the mathematics of this curve is rather an interesting one. What is true is this, that the height of the water when both holes are open is equal to the height that you would get from number 1 open plus the height that you get from number 2 open. Thus, if it's a trough, the height from 2 is negative and cancels out the height from 1. So you can represent it by talking about the height of the water. But it turns out that the intensity in any case, for instance, when both holes are open, is not the same as the height, but it's proportional to the square of the height. And it's because of this fact that we're dealing with the squares that we get these very interesting curves.
Yeah, well, whatever. So he's just pointing out the volume is twice as much at the same height, twice as much volume. intensity is just saying what did it add up to. But anyway, so again, it's just pieces. So again, I'll point out this whole video, this whole hour lecture is on this one subject, as if, and so just to be clear how important this is to their quantum mechanics. Out of 7 hours of a discussion, Feynman spent a whole hour talking about this. And again, just recognize he's not even talking about the real pattern. Because he can't talk about the real pattern. That's the joke here, right? He can't talk about the real pattern because none of this applies to creating the real pattern in photons.
All right, now, we erase the machinery and start over. This time, we start with electrons. We have a filament here, tungsten plate, holes in the tungsten.
So again, electrons is a really complicated experiment, doing it with electrons. Photons, really easy. So, but he's not going to use photons because I think he knows the pattern's not right, for one reason. And I don't know, I guess it somehow proves the point more that it applies to everything. Well, but anyway, so they didn't even, at the time Feynman made this video, they didn't even have a good electron experiment. And they still really don't. That proves this, that it creates the right pattern. Okay, the one with the empty spots here. That only shows up if, depending on how you detect the electrons. If you detect the electrons using a substance that also detects X-rays, you'll get the bars in the right place. But if you use it detecting electrons that in a way that X-rays can't produce the same result, that is, you've eliminated the possibility that an X-ray caused the effect, you won't get this pattern.
Plate, and for a detector, any electrical system was sufficiently sensitive to pick up the charge of an electron arriving with whatever energy to source that. Or if you would prefer, we could use photons, and this is a black paper with a hole in it, 2 holes in another sheet of black paper. Paper isn't very good because the fibers don't make a sharp.
Right. So he's already qualifying how you can't do this simply. You can't just sit there and say they're all the same experiments, all the same mechanics, because different things will affect the outcome. Little rough edges of the photons matter. For electrons, obviously, it's going to be how much charge there is on the substances you're shooting the electrons through. The fact that the electrons hate each other and are moving apart. I mean, lots of things to make the experiments very different. So there's no point in saying it's all the same thing.
Oh, so use something better. And here, for a detector, a photomultiplier that can detect the individual photons arising. Now, what happens with either case, and I'll discuss only the electron case, the other case is exactly the same, the case with photons.
So he says it's exactly the same. Now, we know the pattern's not exactly the same, so right there we're already in trouble. He doesn't even have the right pattern, and he's saying it's all exactly the same. Why would we think electrons and photons are the same? Now, we would think there's something similar about throwing a baseball down a cliff and throwing a lead house smashing ball down a cliff, and they're going to bounce different.
Is this first? Now, what we receive in this electrical detector with a sufficiently powerful amplifier behind it are clicks. Click, 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 and so on, with the source here. Lumps. Absolutely lumps. When the click comes, it's a certain size, and the size is the same. If you turn the source weaker, the clicks come further apart, but it's the same size click. You turn it up, they go click, 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 and a jam.
Yeah, electrons come in clumps. Okay, so he's just establishing its clumps.
The amplifier. So you have to turn it down enough that there aren't
lumps.
Too many clicks for the machinery that you're using to detect. Next, if you will to put up another detector here and listen to both of them, you never get 2 clicks at the same time, at least if the source is weak enough so that, because of the precision with which you measure at the same time. If you cut down the intensity of the source so they come few and far between, they never come a click in both detectors.
All right, so they've never done this experiment, so this is the catch here, right? So he's saying there's never a click at both locations. They never did that experiment. They never sat there and detected whether an electron lands here or an electron lands here when they adjust how many electrons are going through the experiment. So they never established that. They're establishing it by just doing the experiment and saying how many clicks do they get in this box. Okay, but they never established that they have a slow enough rate of electrons that they never get 2 clicks at the same time in the 2 slits. So, it's all this stuff is important, and like I said, there's no, all of these claims are made without any analysis of exactly what experiment was done and how well it was done.
So that means that the thing which is coming comes in lumps. It has a definite size and it only comes to one place at a time. All right, so for electrons, or for photons.
So he said, or for photons again. The rules really aren't the same. The idea of sending one of these things at a time is different. Detecting them is different. So, why keep saying it?
We'll just use it. It comes in lumps.
See, I would argue you can't possibly break an electron. So fragments of electrons can't be going to the locations, and there's no way for electrons to create the pattern, the real double slit pattern, because there can't be four sources. There can only be two. And they are not interfering with each other. They're interfering with the electrons on the slit surfaces, just like the photons.
And therefore, what we can do is the same thing as we did with the bullets. We measure how many come, we measure the probability of arrival. What we do is we hold the detector in a certain place. Actually, if we wanted to, although it's expensive, we could put detectors all over at the same time and make the whole curve simultaneously. But let's suppose we put it...
Yeah, or you could put film down that only detects them. You can do lots of things that they never did. Yeah.
A certain place, and we measure at the end of an hour how many electrons came, and we average it. By the way, if I put detectors all along the back here, when one comes, it comes into one, but not from others. It just one goes off, and the other goes off, and this goes off, and that one goes off. Just like with bullets. And we measure then the probability of arrival of the electrons. And what do we get? The number of electrons that arrive. The same kind of an N12 as before. This is what we get for N12. N12 is this is what we get with both holes open. And that's the phenomenon of nature.
So again, he's claiming to get the pattern, but it's not the right pattern in the first place. And the second place, the electron experiments there's lots to critique in those experiments. So again, the photon experiments are quite simple and the outcomes are obvious. And he'll make a claim soon that, again, has been established by no experiment.
He produces the curve, which is the same as you would get from an interference of waves. But she produces...
So again, it isn't the same. I'll just keep emphasizing it. The double slit pattern is not the same as the two-wave pattern. The two waves can't create the more complex pattern. Can't be done with two waves.
The curve for what? Not for the energy in a wave, but for the probability of arrival of one of these lumps. The mathematics is simple. You change I to N, and you have to change H to something else, which is new. You call it something because it's not the height of anything, but in order, this curve has a simple mathematical form. There's an A, which can be represented as an A1 plus an A2, which we call a probability amplitude, because we don't know what it means. Which to arrive from hole 1 plus the probability amplitude to arrive from hole 2, and you add the two together to get the total probability amplitude to arrive, and square it. Just direct imitation of what happens with the wave, because we've got to get the same curve out, so we use the same mathematics. Let's find out, I better check on one point, though, about the interference, I forgot to say. What happens if we close one of the holes? Let's try to analyze this interesting curve, which now, for electrons, I erase all the stuff with the light. Well, everything with light is erased. And now we're talking about electrons. This curve isn't important in our case. This is the number which arrives. Now, we would like to analyze this curve. And we try this. We say maybe it comes, we can analyze this by thinking if the electron through this hole or through the other. So we can close one hole and measure how many come through hole number 1, and we get that curve. Or we can close this hole and measure how many come through hole number 2, and we get that curve.
Right, and the two curves would be on top of each other. So let's just re-emphasize that. They wouldn't be separated. They would be almost imperceptibly in the same location.
And these two added together is not this, and so this is not the same as N1 plus N2, and it does show interference.
So he says it shows interference. It shows that the electrons coming go through one slit or the other slit are not the same path, and that's all it shows. It doesn't show anything else. It's except that there's a difference in the path taken.
It shows interference, and in fact the mathematics is given by this funny formula that the probability of arrival is the square of an amplitude, which itself is the sum of two pieces.
Yeah, well, again, the squaring the amplitude is that the formula doesn't say anything at all, right? I mean, n1 and 2 equals a1 and 2 squared. Doesn't say anything, except in my opinion, it says, well, why is it squared? Well, it's squared because there's 4 sources, not 2.
Now, nobody. The question is, how can that come about? That when they go through hole 1, they would be distributed this way. When they go through hole 2, they would be distributed that way. How can it be that when both holes are open, you don't get the sum of the two? Instance. If I hold the detector at this point here, I get practically nothing. If I close one of the holes, I get plenty. If I close the other hole, I get something.
So again, he has these 2 in the wrong location, so obviously that doesn't make any sense. But the idea again is that there's obviously pieces, heads going through one thing, feet going through the other thing, and yes, you can't see heads alone, you can't see feet alone, but when you combine heads with feet, you will see something.
If I leave both holes open, I get nothing. If I let them go through both holes, I don't come anymore. Well,
so that experiment's not been done. So the point is that they say it does this thing where when you have one slit open, there's light in a location, and then I open the second slit and there's no light at the location there was light. That they've never proven with any experiment, that something gets less light. The only evidence is that some locations get brighter, not that some locations get darker. So they've never established it as a fact that anything ever gets darker. They've only demonstrated with experiments that something gets brighter.
The point in the center, you can show that that's higher than the sum than it was in the other case, than the sum of these two. I get more here when both holes are open.
We've already established that it's squared, so we've already established that it isn't contribution plus contribution. There isn't 1 plus 1 equals 2. There's 1 plus 1 equals 4. So somehow the light's making more at the on locations. There's no evidence that it's making less light at the off locations.
Then I would get with either one of the two closed. Now you might think that if you were clever enough, you could argue that they have some way of going around through the holes back and forth, and they do something complicated, or it splits in half and goes through the two holes, and so forth, in order to explain this phenomenon.
Yes, that's how you explain it with photons. You say it splits in half and creates 2 wave function probability waves, and they interfere with each other. You know, that's your crap.
Nobody, however, has succeeded to get an explanation of this that's satisfactory, because the mathematics...
Okay, so I'm just saying that obviously he couldn't know I would exist in the future and properly explain the experiment. And it's been properly explained. Photons are big objects because they have a very large polarization. They're made of little tiny quanta. When you put them through some kind of, what do you call that, obstacle course, pieces of them fall off. They get beat up going through the process you're putting them through. You're putting them through a little bit of a grinder. They get ground up, they break into pieces, and the pieces go to different locations, and sometimes you put pieces back together and sometimes you don't. And that's all there is. It's not complicated at all.
Mathematics in the end is so very simple. The curve is so very simple. I will summarize then by saying...
So let's understand, the curve is so simple. It's not. The pattern isn't simple in the 2 slits. It isn't. It's got this huge complication in it where those little X's are. Big, huge complication. And they have no viable and reasonable explanation. They cannot draw you a picture of why those X's are there.
That electrons arrive in lumps, like particles. But the probability of arrival of these lumps is determined like the intensity of waves would be. And it is in this sense that the electron behaves, as you might say, sometimes like a particle and sometimes like a wave. It behaves in these...
Okay, so this behave things it seems like, that's all he's saying, right? It seems like, it seems like, it seems like, it seems like. And what the physicist really should be looking for is the is like. What is it really is like? What can we know about it? And again, if they did any kind of analysis of their own wave picture, they would know that, well, that wave doesn't mean anything unless I define it, right? Is 1 clump of the wave a photon? Is 4 clumps of what's a photon? Any analysis will demonstrate that it's more complicated than just saying photon. All right, probably enough. We'll save the rest for the next time and such, and so forth and whatnot. Hopefully just one more, but might take two. That doesn't, this is a hugely important, and this is the foundation of their quantum mechanics. This is the foundation of all their woo, is this experiment. And I'm just demonstrating how little care they've taken to look at it. And I could play the Fermi Lab guy again is saying you have to believe in general relativity. It's so factual and real, and is again the defenses are so sloppy and irrational. In terms of, he tells us again about the Eddington experiment. You can't even describe it correctly. Like Eddington saw light from a sun behind our sun, from a star behind the sun. No, it wasn't behind the sun. I mean, they can't even get these foundational simple experiments right. They can't describe them accurately. And you trust these people when they can screw up something this simple. Why do you trust them? Anyway, it's a rhetorical question, I guess. There's no point in asking the question, right? Why? Because you want to believe in the woo, I guess. You like this silly, stupid explanation. Oh, it's just random. God does play dice with the universe. You want to believe that? Ugh.